Welcome back to the channel. Today, we are diving deep into one of the most precise and versatile welding processes out there. Gas tungsten arc welding, better known as TIG welding. Whether you're working on aerospace components, stainless steel fabrication, or artistic metalwork, GTAW is the gold standard for quality and control. By the end of this video, you'll understand exactly how it works, when to use it, and what makes it so special. Let's get started. GTAW stands for gas tungsten arc welding, but you'll hear most people call it TIG welding, that's tungsten inert gas. This process was developed in the 1940s for welding magnesium and aluminum in aircraft manufacturing. Unlike other welding methods, TIG uses a non-consumable tungsten electrode to create the arc. The tungsten doesn't melt into the weld, it just creates the heat. A separate filler rod is fed into the weld pool manually, giving you incredible control over the process. The entire weld area is protected by an inert gas, typically argon or helium, which shields the molten metal from atmospheric contamination. Let's break down the equipment you need for TIG welding. First, the power source. TIG welders can use either AC or DC current, depending on what you're welding. You'll need a TIG torch that holds the tungsten electrode and has a connection for the shielding gas. The torch also has a ceramic cup or nozzle that directs the gas flow over the weld area. Next, you need tungsten electrodes. These come in different types and sizes: pure tungsten, thoriated, serrated, or lanthanated. Each has specific applications. You'll also need filler rods in various diameters and materials to match your base metal. The gas supply is critical. Most commonly, we use pure argon for steel and stainless steel, or an argon-helium mix for aluminum and thicker materials. You'll need a regulator and flow meter to control the gas. Finally, you need a foot pedal or finger control to adjust amperage on the fly during welding. This gives you that precise heat control TIG is famous for. So how does TIG welding actually work? When you strike an arc between the tungsten electrode and the workpiece, temperatures reach over 11,000 degrees Fahrenheit. This intense heat creates a molten weld pool on the base metal. As you move the torch along the joint, you manually feed the filler rod into this pool. The filler melts and fuses with the base metal, creating the weld bead. Meanwhile, the inert shielding gas flows through the torch and blankets the entire weld area. This is crucial, it prevents oxygen and nitrogen from the air from contaminating the molten metal, which would create weak, porous welds. The welder controls three things simultaneously: the torch position and angle, the filler rod feed, and the heat input through the foot pedal. This is what makes TIG welding challenging but also incredibly precise. You have complete control over every aspect of the weld. One unique aspect of TIG is that we can use either AC or DC current, and the choice matters. DC electrode negative, or DCEN, is used for welding steel, stainless steel, and most other metals. The electrons flow from the electrode to the workpiece, creating deep penetration and a stable arc. AC current is primarily used for aluminum and magnesium. Why? These metals form an oxide layer that melts at a much higher temperature than the base metal. AC provides a cleaning action that breaks up this oxide layer during the electrode positive portion of the cycle, while still providing good penetration during the electrode negative portion. Some modern machines offer advanced AC waveforms that let you adjust the balance between cleaning action and penetration, giving you even more control. Let's talk about tungsten electrodes because choosing the right one matters. Pure tungsten, with its green color code, is mainly used for AC welding of aluminum. It forms a clean bald end when heated. Thoriated tungsten, marked in red, contains 1-2% thorium oxide. It's excellent for DC welding and provides easy arc starting and stability. However, thorium is mildly radioactive, so you need to handle grinding dust carefully. Serrated tungsten, in orange, is a great all-purpose electrode that works well on both AC and DC at lower amperages. It's become popular as a thoriated alternative. Lanthanated tungsten, in gold or blue, offers excellent arc starting and longevity. It works across a wide range of applications. The electrode tip preparation is also critical. For DC welding, you grind it to a sharp point. For AC, you use a bald or rounded end. The grind marks should run lengthwise, never across the electrode. TIG welding's versatility really shines when you look at what you can weld. It's the go-to process for stainless steel in food processing, pharmaceutical, and aerospace applications. The clean, precise welds are corrosion-resistant and visually appealing. For aluminum, TIG is often the best choice, especially for thinner materials. You get clean welds without the spatter and porosity issues of other processes. It's excellent for exotic metals like titanium, used in aerospace and medical implants, and magnesium alloys. You can weld copper and copper alloys, though the high thermal conductivity presents challenges. TIG even works on dissimilar metals, welding stainless to mild steel, for example. The process works on material as thin as 0.01 inches up to several inches thick with multiple passes. However, TIG isn't ideal for everything. It's slower than MIG or stick welding, making it less efficient for thick structural steel or long production runs. Why choose TIG welding? First, weld quality. TIG produces the highest quality, most precise welds of any arc welding process. The welds are clean, strong, and visually superior with minimal spatter. Second, control. You have independent control over heat input and filler metal addition. This means you can weld extremely thin materials without burn-through, or make beautiful cosmetic welds on visible joints. Third, versatility. As we discussed, TIG works on more metals than any other welding process, from steel to aluminum to exotic alloys. Fourth, clean welding. There's no slag to chip off, minimal spatter, and no flux residue. This means less post-weld cleanup. Fifth, you can weld in all positions, flat, horizontal, vertical, and overhead, with the same quality results. And finally, when done correctly, TIG welds require little to no finishing work. The weld is the finished product. TIG welding isn't perfect for every situation. The main drawback is speed. TIG is significantly slower than MIG or stick welding because you're manually feeding the filler rod and controlling everything by hand. This makes it less cost-effective for high production environments or thick structural work. It requires high skill levels. Coordinating the torch, filler rod, and foot pedal while maintaining proper technique takes considerable practice. The learning curve is steep. TIG is also sensitive to contamination. Drafts can blow away your shielding gas, and any oil, rust, or dirt on the metal will compromise the weld. Surface preparation is critical. The equipment cost is higher than stick welding, and you need to purchase and manage shielding gas supplies. Finally, it's not ideal for outdoor work. Wind can disrupt the gas shield, and the process doesn't work well on rusty or dirty material like stick welding does. Safety equipment and precautions layout. Auto darkening welding helmet, shade 10-13 lens, flame-resistant welding jacket and gloves, ventilation fan, fume extractor, safety glasses, proper leather TIG gloves, gas leak detector, grounding cable, warning signs for over-radiation and ventilation requirements, organized safety poster-style layout, bright warning colors and clear labels. Where do we see TIG welding in the real world? Aerospace is a huge application. Aircraft frames, engine components, and fuel systems all rely on TIG for its precision and quality on aluminum and titanium alloys. The automotive industry uses TIG for exhaust systems, roll cages, and custom fabrication where appearance and quality matter. Race car fabrication relies heavily on TIG. In food and beverage processing, pharmaceutical manufacturing, and chemical plants, TIG is the standard for stainless steel piping and vessels. The clean, corrosion-resistant welds are essential for these sanitary applications. Bicycle frame builders and custom motorcycle fabricators love TIG for creating beautiful, strong joints on thin wall tubing. The art and sculpture community uses TIG extensively. The precise control allows artists to create intricate metal sculptures and installations. Nuclear power, shipbuilding, and medical device manufacturing all depend on TIG welding for critical, high-quality joints where failure is not an option. Let me share some fundamental technique tips for beginners. First, torch angle. Hold the torch at 70 to 80 degrees from the work surface, leaning in the direction of travel. The filler rod should enter at about 15 to 20 degrees. Maintain a consistent arc length, typically 1/8 inch or about the diameter of your tungsten. Too long creates a wandering, unstable arc. Too short risks contaminating the tungsten. Use a walking the cup technique on pipe welds. Rest the ceramic cup on the work and rock it along the joint. This stabilizes your hand and maintains consistent arc length. For filler rod technique, dab the rod into the leading edge of the puddle in a rhythmic motion. This creates the characteristic stacked dime appearance of quality TIG welds. Start with lower amperage and increase as needed. It's easier to add heat than to fix a burn-through. Practice your pedal control. Feathering the amperage lets you control heat input precisely, starting high to establish the puddle, then backing off to maintain it. Keep the tungsten and filler rod inside the gas shield at all times, especially when stopping. Pulling them out while hot will oxidize them. Let's troubleshoot common TIG welding defects. Porosity, those small holes in the weld, usually comes from contamination. Check your shielding gas flow rate, make sure there are no drafts, clean your material better, and verify your gas supply isn't contaminated. Tungsten contamination happens when you touch the tungsten to the puddle or let the filler rod contact the electrode. You'll see black spots in the weld. The fix: re-grind your tungsten and practice better technique. Undercut, that groove along the weld edge, means you're moving too fast or your amperage is too high. Slow down and reduce heat. If you see excessive oxidation or discoloration, your gas coverage is insufficient. Increase flow rate, check for leaks, or add trailing shields for materials like stainless steel and titanium. Cracking can result from welding too hot, cooling too fast, or using the wrong filler metal. Match your filler to your base metal and control your cooling rate. Inconsistent penetration usually points to fluctuating travel speed or inconsistent arc length. Focus on maintaining steady speed and torch height. Once you've mastered the basics, there are advanced techniques to explore. Pulse TIG uses pulsating current that alternates between high peak amperage and low background amperage. This reduces heat input, minimizes distortion, and allows better control on thin materials. Keyholing is a technique for full penetration welds on pipe or critical joints. You create a small hole through the material and fill it as you progress, ensuring 100% penetration. Back purging is essential when welding materials like stainless steel and titanium. You flow inert gas on the backside of the weld to prevent oxidation on the root side. For autogenous welding, you don't add filler metal at all, you simply melt the base metals together. This works on thin materials and creates minimal weld reinforcement. Some welders use advanced techniques like lay wire or hot wire processes for increased deposition rates while maintaining TIG quality. Remote amperage control using a fingertip slider or advanced foot pedals gives you even more precise heat control during complex welds. If you are interested in learning TIG welding, here's my advice. Start with the right equipment. You don't need the most expensive machine, but get one with both AC and DC capability if your budget allows. Start with a machine rated for at least 200 amps. Begin practicing on mild steel with DC. It's the most forgiving material and teaches you the fundamentals without the added complexity of arc aluminum welding. Invest in proper safety equipment from day one. Don't compromise on your helmet, gloves, or ventilation. Practice material preparation. Clean metals weld better. Use a stainless wire brush dedicated to the metal you're welding. Never use the same brush for aluminum and steel. Start with simple bead on plate exercises before attempting joints. Master your puddle control, arc length, and filler addition before tackling T-joints or corner welds. Take a class if possible. TIG welding is difficult to learn from videos alone. Hands-on instruction from an experienced welder accelerates your learning tremendously. Finally, be patient. TIG has the steepest learning curve of common welding processes. It takes time to develop the coordination and muscle memory. And there you have it, your complete guide to gas tungsten arc welding. We've covered what TIG is, how it works, the equipment you need, materials you can weld, advantages and limitations, safety considerations, applications, techniques, troubleshooting, and how to get started. TIG welding is an incredibly rewarding skill. Yes, it's challenging to learn, but the precision, quality, and versatility make it worth the effort. Whether you're interested in aerospace, automotive, fabrication, or artistic metalwork, TIG opens up incredible possibilities. If you found this video helpful, please hit that like button and subscribe to the channel for more welding content. Drop a comment below if you have questions or want to share your TIG welding experiences. Are you interested in learning TIG? What's the first project you want to tackle? Let me know in the comments. Thanks for watching, and I'll see you in the next video. Stay safe and keep welding.